And let's see this one.
Okay, looks like we're ready to go. So it's a great pleasure to welcome back Diego Cantor to Western. Diego finished his PhD a couple of years ago in my lab. He's been working since at a weight lab in Toronto, where he is the Chief Technical Officer. He may tell you a little bit about what a weight lab is all about and why deep learning is important in what he's doing. So apparently we're going to be talking about chairs.
Yeah. So thank you very much for the invitation. We can leave it on, Terry, for a little bit. Thank you. So thank you very much for the invitation. I'm really happy to be here again. And I would like to introduce you to these four chairs because these are the real protagonists of my talk today. They have a very important message to give us, to all of us, and that is how to deal with small data sets when you're trying to do deep learning. To show you what I mean, I prepared a little example from one of the projects I developed during my postdoc. So here we go. So this is James, my imaginary patient, and he has been complaining of having headaches and vision loss. So James goes to the hospital and their doctors take an MRI and they find that James has a tumor in the occipital lobe, which is consistent with his symptoms. So in order to provide care, it is important and necessary to determine what type of tumor this is. And the only way to do this is by extracting a biopsy. So a biopsy is a very invasive procedure. They have to open a hole in your skull. They have to drive a needle to the location of the tumor and extract tissue. So in James' case, the tumor that he had is an oligodendroglioma. And because now we can see inside his brain, we can determine, depending on the grade of the tumor, what type of treatment are available for him. So would it be a good thing to avoid the biopsy altogether? So what if we could take the MRI here, examine the tumor, and try to predict features here in the histology to be able to know what's going on. So that's the premise of my project. So let's think about it for a little. Why do we want to do this? Because if we do this, then this method is not invasive, so we don't have to have the surgery. We can have early detection of any pathology just by scanning the patient with the MRI. And we can provide information for diagnosis and also for the effectiveness of the treatment or the progression of the disease. So now I'm going to show you my proof of concept, how I approach this problem. So this is what I want to do. So I have my MRI, and here I have, it's color-coded, it's like an RGB picture, and each channel of this picture has a different type of MRI. I have, for people who work with MRI, those terms are very familiar. I had these three types of MRI, and by combining them and registering them together, then this is the image that I have. And what I want to do is I want to predict something like this. This is the corresponding slice taken from the histology, and this is color-coded. Here I'm looking at neuronal density. So what I want to do is I want to take this as an input, and I want to predict neuronal density. And this is the first step towards looking into the structure of the tissue just from the MRI. So in this case, in this area where I have no neurons, I want to predict that there are no neurons. And in this area where I have neurons, I want to predict that there are, the neuronal density is high. So to do so, I used deep learning. This is the method that I use. It's called fully convolutional networks. And here we have a picture of a dog, a cat, and a sofa. And the idea is that for every pixel in the image, you're going to have a prediction pixel-wise. And you can see that here. And this method has been used in many different problems in computer vision. Here we have the semantic segmentation, which is the one I just described. So for every pixel in the image, I'm going to describe, in this case, if it's a horse pixel, jockey, rider pixel, or a background pixel. But here, for instance, it's also been applied to detecting estimation from monocular cameras. So here you can see the ground truth for this image, and this is the estimation that the network produces. And this is another example for boundary detection. So I read the paper, and then I adapted the network. And this network had 42 layers, which is slightly lesser than the original paper. So I implemented this network, 43 layers. And here what I did was to take my MRI and I created patches of 28 by 28 pixels, and then I tried to predict the corresponding neuronal density in the histology. So this is what the network looks like while it's training. Maybe you can turn off the light now. So you see the first column shows the ground truth. So this is the histology. And the second column corresponds to the prediction. So you can see how the network slightly starts differentiating. And for every different example of the ground truth, it tries to match that ground truth. So I did about 900,000 examples, maybe a little bit more than that. And this is what the network is producing after about 300,000 iterations. So you can see here in an area of low neural density, the network is able to predict low neural density. Here we have medium neural density and the network tries to match it. But we have issues with regions of high neural density. So for instance, this region here, the network didn't do a good job. But again, it's not fully trained. All right. So when I put everything together, so I used, again, 28 by 28 patches, and then I put everything together to try to get a prediction per slice. And then I obtained these beautiful images. So you can see here the MRI, and this is the ground truth. And you can see here how the network really does a good job predicting these regions. So I'm showing you the best examples that I got. This is another example. Here is the input. This is the ground truth. And this is the deep learning prediction. And here in the ground truth, remember, this is histology. So when you process the tissue, you lost tissue. However, because I'm obtaining this prediction from the MRI, this is before processing the tissue, then I can obtain the tissue that was lost here. So this is very interesting. And this is a detailed view. So you can see here how some layer in the cortex can start appearing here in the prediction. So this is very interesting. But then I showed these results to my supervisor, and I had a similar conversation to the one here on the board. The conclusion is, okay, Diego, you just only have 20 patients, just only 20 patients. And then I was like, but I have 1 million examples. Isn't this sufficient to use deep learning? And then the problem is that, yes, from the machine learning perspective, you have a lot of information, and maybe you can execute these models. But the problem is the problem that you're trying to solve. If you're trying to predict neuronal density for the entire human population, well, maybe you need more data. It's a very different problem to the case where you're trying to solve something that occurs very specifically in the population that you are analyzing. So that's the first roadblock. So how much data do we need? Well, it depends on the problem you're trying to solve. Also, there is a generalized fear of overfitting. We have models that have high capacity. So you have networks that have many layers, many parameters. And when you have very little data, you most likely are going to overfit. So in the rest of my presentation, I to try to address that fear and look for alternatives. So we get to the chairs now. Can turn on the light. Okay, so after that conversation, I had 4 choices. So 4 chairs, 4 choices. So option number 1. What was I thinking? I just read 2 papers about deep learning. I don't know anything about this stuff. There are people who are way more intelligent than me. I should go back to what I know. What a waste of time. I need a drink. Okay. Option number 2. I need more data. But I have to wait until people get sick to get more data. I feel bad about that. So how can I get more data from the data that I have? What about, you know, that method, dictionary learning or manifold learning? Oh, actually, there is a person who is very good in my lab at that. You should go and talk to that person. Option number 3. Okay, hold on, hold your horses, count to 10, take a deep breath. You are an engineer. And an engineer solves problems, and you are very good at solving problems. And you are a PhD student. You are much better. So, think about the problem. How can I make this problem easier? Can I impose constraints? What about a smaller problem? Maybe I try to I try to get too much. So let's focus on something simpler. Option number 4. Well, this is just my first try. I just tried this architecture, but deep learning has so many things to offer. Maybe I should try something else. So many different models to try, and you have autoencoders, and then you have, many different architectures. Maybe I don't know anything about it, but I can learn it, and I can, work on the method. So there you go. Those are the 4 choices, and the rest of my presentation, I want to analyze what these mean and how we can use them. So, the first option is the traditional chair. So the traditional chair, the traditional approach represents safety, represents something that we already know. In my PhD, I didn't know anything about deep learning. I worked with support vector machines. So for me, it would have been a lot easier to come back here and say, well, you know what, I just need to graduate, just throw in this method. But then the problem with that in a personal level is you've already been there. You're a researcher, you need to be a bit risky, get to know more, become a better researcher. Having said that, deep learning probably is not the best solution to your problem. So you need to be aware of the trade-offs. In my particular case, the trade-off is that if I do something traditional like support vector machines, I have to become very good at creating good features. And actually, in my PhD thesis, I have 1 chapter, almost 2 chapters dedicated to how to create good features. So that's part of the trade-off. In deep learning, the network learns the features for you. Having said that, in traditional machine learning, most methods are not compositional. I'm going to explain what I mean. In deep learning, most methods are compositional. So this is a criterion that you need to take into account in order to determine if deep learning will work well for your problem. So here are 2 examples of what deep learning is good at. So these are compositional problems. We want to detect faces, for instance. And now we know that deep learning goes about it by looking at low-level features, combining them, producing facial features, and then by combining them, we can create faces. But human perception goes beyond that. It's not only about recognizing another human being. We can also know if that person is a family member or someone we had never spoken with. And when we talk about language models, language representation, we can start with hearing the sounds, forming the phonemes in our heads, and then creating the words. But it's beyond that, It's the difference between really or really. So you see, voice is more about, it has many other levels of composition. When we talk about specialized human perception, like here, I decided to show you this text. This is from a textbook for pathology in order to identify the type of tumor that my imaginary patient had. So let's take a look here. It says that well-differentiated oligodendrogliomas show uniform round cells. So here you have uniform round cells that are interrupted by a dense network of branch capillaries. And they show with the arrows what they mean by those networks of branch capillaries. So for me, I cannot perceive that because my knowledge is not specialized, but for someone in the pathology department, probably this makes a lot of sense. So again, deep learning is not probably applicable to every single problem. We need a lot of data, and when we have a lot of data, then we can go beyond the performance that is achieved right now with traditional methods. But take into account that the performance is also tied to the problem. Certain problems obtaining an accuracy of 85% could be okay, and that's acceptable, and that's defendable, and you can publish your paper. In some other problems, maybe you need to go higher in order to be. So choose your method depending on the problem and depending on if it's compositional or not compositional. Okay, so now we go to the second chair. This is the data chair. Thank you, Terry. So again, when we work in the medical domain, it's very difficult to acquire data, so we have to become very good at finding ways of creating more data. So the good news is that, it happens everywhere. We are not alone. This is an open letter to Jan LeCun, one of the main machine learning researchers in the world right now. And here is showing us that generalized deep learning seems to be proprietary to big companies that have big data and a lot of resources. Most of medical research occurs in this quadrant where you have small data, and we're trying to create specialized learning here. The Holy Grail, what we all want is to be on this quadrant. That is the Holy Grail. We want to do specialized deep learning with lots of data. So this is our reality. So if you don't have a lot of data, don't feel bad about it, because we are all in the same quadrant. So the first thing that I tried in my project was to use a method called data augmentation. So at the end of the day, it doesn't matter if the pathology is oriented in a certain way, I should still be able to recognize it. So I use rotations, 90-degree rotations here, and for every element that I have in my training set, I created 8 in total. So this is one possible way of going about it with data augmentation. You apply a fine transform that makes sense to your problem in order to create more data. This is another project that I worked on during my postdoc, and this is about recognizing anatomy in ultrasound. So in this particular case, again, it was very difficult and very lengthy to try to obtain a large data set. So what we did was to create synthetic data set. Here. So here we have a spinal phantom, and we're acquiring lots of images, and we're training our deep learning network in recognizing features on these phantoms. So when you work with phantoms, you can acquire as much data as you want. There is no limits to the amount of data that you can create. However, the argument here is that there's a limitation for how well these phantoms represent the actual anatomy in humans, but this is a good start. You can train on models like this and then go to the small data set of human data that you have, and then you would have a good starting point to start training that network. And here I have 2 slides of current methods in deep learning that you can use to create more data. So the first method is generative adversarial networks, or GANs. And here the idea is it's a game of the cat and the mouse. It's the struggle between the person who tries to counterfeit money and the central bank. So we have 2 networks. One network is the generator network, the one that's trying to counterfeit or deceit, and the other network is the discriminator network. So the algorithm works a very simple way. Here we have an example where this generator network is trying to handwrite digits, and the task of the discriminator network is to determine if the digits are real or not. So the first step is we're going to freeze the generator network. That means that there is no training, and the generator just produces examples. And then we train the discriminator. Because the generator hasn't been trained, then the samples that we get here are really bad. So the discriminator gets really good at differentiating between real digits coming from the real data set and fake digits. In the second step, we freeze the discriminator network. So there is no learning here. And then what we're going to do is we're going to try to train the generator to deceit the discriminator. So in this step, the generator network is going to produce an example, and depending on the output here, if the discriminator was able to discern that it was a true example, a real example, a fake example, then we're going to use that information to improve the generator. This cycle repeats. We train one network at a time, and after many iterations, we get to the point where the generator becomes really good. So you can have an input here, and then you can create any possible example in your data set. So this is a possible way of creating data. Another method is known as variational autoencoders. So here the architecture is a little bit different. This is an example. This Eugene Park, I think he's a postdoc at University of North Carolina, Chapel Hill, and this is an internal report that he wrote. And he's showing us here, these are synthetic brains generated with variational autoencoders. So these are not real images. So he trained a variational autoencoder in such a way that now he can create this type of images. And clearly, these images have a lot of detail and we can use them for research. So the network that he used looks like this, but of course, I don't expect you to even be able to read because this is a very small diagram, very abstract, so I'm going to explain it with cats. So a variational autoencoder is composed by two networks or two parts. On one hand, we have the encoder, and on the other part, we have the decoder. And the task of the encoder is going to try to predict a latent or a hidden variable here. But this variable is stochastic. That means that it's trying to represent the distribution, an internal distribution for examples presented here. So if we are very good at estimating this distribution, which is usually embedded in a low dimensional manifold, then later on we can use the distribution and sample this distribution to produce examples from that distribution. So the way it's trained, because we have this input, then we do the estimate, and then we can corroborate by sampling from the distribution if that sample corresponds to the input. So we do that first, and then once that we have learned the distribution, then we can sample we can sample the distribution at any point, and by doing so we can spawn the whole manifold. So this is another way to create more data. And then the question is, what about labels? So I don't really have a lot of time to go into detail, but I want to refer you to this website. It's done at csstanford.edu, and they have very interesting methods to deal with labeled data. So once that we create more examples, so who is going to label those examples? Is it the radiologist? We go back with 1 terabyte of data and say to the radiologist, hey, can you help me here? Well, maybe that's not realistic, but for instance, we can use active learning in which we present key examples to the radiologist, and he can help us with those examples, and we can use those key examples to label everything else. But that's just one of many possible methods, so I will share my presentation later with you, and then you can go to this website. It has amazing resources that explain how to label data. Okay, so now we move on to the third chair. This is the problem chair. Just 1 second. All right. So here I want to talk specifically about what I did in my project, so you have an idea of how you can do it in your project. So in my project, I was very ambitious. I was trying to estimate neuronal density, and I had 10 classes. So my labels went from 0.1 to 0.2 to 0.3 to 1, meaning that in that voxel, the density was 1 or 0.5 or 0.3. That was the percentage of neurons in that particular voxel. So I had 10 classes. So why is that ambitious? Because my data set is small, and what I observed and what I showed you before is that we are not really good at estimating high neural density. You can see here that low neural density works, medium neural density works, but high neural density didn't work. Why? Because I didn't have sufficient data points for that particular class. And this is reality. This is what happens with data sets. The labels are not even. We have always more one type of data than the other. So instead of having 10 possible classes, I said, well, what about dividing the problem into low, medium, and high? So when I do that, then the accuracy of my system went up because I was being less ambitious. I wasn't trying to predict with this level of detail the density, but rather I would have a very coarse estimation of density, which is still useful. Another way to modify your problem with the small data set that you have is by imposing a priori knowledge, so knowledge of your particular domain. So because I was looking at cellular structure, then I knew that this configuration is more likely than this configuration. So here you have high neural density enclosed by medium neural density enclosed by low neural density. And that is the kind of topology that you find in cellular architectures. Whereas here, this is something that rarely happens. So what I did was to modify, what we're trying to do was to modify my loss function. So this is what the network tries to optimize. And usually the loss function compares your prediction y here to the ground truth. And there's some function here that compares these two. And this is pixel-wise. Okay? But what if I impose topological constraints? I can then say, okay, the loss is going to be lower if the topological constraint that I have appears. So that reduces the loss. And I'm going to penalize the loss, or the loss is going to increase if a topological configuration that I don't want then appears. So this is a possible way where you can constrain your problem and you can do more with the little data that you have. And then the third case is, okay, let's look for alternative problems. So as I showed you before, I was able to show here the tissue that was missing after processing. So what about, instead of trying to solve the problem of predicting neural density, I changed that problem and then now I'm trying to predict the tissue that was lost during histological processing. And what can I do with that? So think about it. You have the MRI, right? And you can predict this tissue that was lost, then maybe you can use this method helping algorithms that try to reconstruct histology in 3D. So you see, there is everything that you do at the lab is never lost. There's always a way to find something interesting that can be applicable. Okay, and we finally got to the fourth chair, and that's the method. So I want to present, maybe we can, sorry. So I found this, while I was doing research for this talk, I found this very interesting paper. This was published in the Scientific Reports. I think this is a journal associated with Nature. And here they are showing us a deep learning tool to detect cancer. So this is the original histology here, and this is the color-coded prediction. And these areas in red correspond to 30%. These areas in red are the areas that are predicted have cancer. And for this particular example, it says here that this area corresponds to 30% of the specimen. So I was very curious about this method, and then I read the paper. They had the additional files where you can get and look at the network that they used. And to my surprise, they used only 8 layers. And I was like, what? 8 layers? I use 43. So how is that they can use 8 layers and obtain the results? So the answer to that is the network that I was using, or this is my conclusion, the network that I was using is a network that is taken from the computer vision domain. So when you take pictures of animals or scenes or landscapes, there is a lot of high frequency detail. You have a lot of information going on in these images. Whereas when you look at histology, images are more uniform. You have cells, there is less variation. There are changes in shape and whatnot, but the amount of high-level information, if you look at the histogram, it would be a very different histogram. So that's the explanation. So I said, okay, when you have a problem, you can go and look for similar research and see what they are doing. And that's what I did here. So how does my method compare to their method? So their method used multi-scale prediction. That means that instead of trying to do a prediction pixel-wise, they take a window and then they make a prediction for that window. And then they go to a different scale. So instead of having this zoom, they go to this zoom, and then they have one prediction for that window. So when you look at multi-scale predictions, the method is very slow. So that was the first comparison. My method was fast, but their method is very slow. However, the trade-off that they made was the efficiency, the computational efficiency. They trade off that with the complexity of the network, the capacity of the network. So yes, I'm going to spend more time doing this because I had to look at multiple scales, but I only used 8 layers instead of using 43. So this is the first thing you can do. You can evaluate what other people in your particular domain are doing. And now I want to, I have 3 more slides talking about overfitting and how we can control overfitting, because again, we work with deep learning models that have a lot of parameters. So there is an agreement in the scientific community that the first thing we can do is we stop the training earlier. So when you have a training error that goes like this and you start seeing that the error starts becoming smaller and the testing error, so these are the examples that were never presented during training. When you test the error and then you see that the error is going up, at that point means that you are losing generalization ability. So that's when you stop. So this is a good way to avoid overfitting, because if you keep going, then the network is going to be really good, really good at classifying your particular training sample. But when presented with other data, it's going to be really bad. So you need to find this step here where the testing error starts increasing and the training error starts decreasing. So this is the first way you can address overfitting. You stop before it happens. Another way is, well, this is a general way, you use regularization. So you have a method that has very high capacity. So here we have a function that can fit a 5th order polynomial here. So if without regularization, then we have a method that overfits. But as you start increasing regularization, you can see that it doesn't matter that we have a very complex method. We have a function that is simpler just because of the fact that we have regularization. And it can be, usually you have 2 ways of going about it. There are many ways, but these are the most common. So you have weights in your network that looks like this. With the L1 penalty, what you do is that most of the weights become 0, and then you have a sparsity constraint. With the L2 penalty, this is the square error. What you're going to do is that the general scale or amplitude of your weights is going to be smaller all across the weights. And now there are networks, there are designs here that you can use to address overfitting. So this is a very common method. It's called a dropout layer. So the idea here, again, is to avoid specialization. You can imagine that as you train your network, there are going to be weights that are going to become critical. Very important. But if you drop out those weights during training, that means that you're never allowing a particular weight to become too important. Or in other words, you have many possible networks here, very thin networks. Every time that you remove a weight, you obtain a different model, right? And you keep repeating that, so you have very thin networks or very sparse networks that, because we're sharing the weights, what that's causing is that you are regularizing every network by using all the other networks. And probably that doesn't make sense, but the point here is that you don't let a particular weight to become too important. And here, you do the opposite. This is a method developed by NVIDIA 2016, and it's called dense, sparse, dense training. So you start with a dense model, then you make it sparse, and then you make it dense again. So the first time that you train this network, it's not about learning. It's about identifying those weights that are important. So you do that, you allow overfitting, and then what you're going to do is you're going to remove those weights that are non-important. By doing so, you obtain a network that is sparse, so with a lot less number of connections, that has about the same accuracy as the initial model. So this model is less complex than this model, but it has the same accuracy. So the problem with this configuration is that it has a high bias. So you have fallen in a local minima. So when you make it dense again, by adding these connections again and training very slowly, you're going to allow the method to move from that local minima into a real minima. And again, this is the paper. They provide a lot more of detail. I don't have a lot of time to explain it, but this is the basic idea. It's very interesting and it's very recent. So this is the end of my presentation. So can we turn on the lights? So my invitation to you is to take these 4 chairs with you. Play with them, make them your own. teach them to your students, take them to your lab and see what happens. And the next time that you hit a roadblock in your research, remember that you have 4 chairs and 4 options. Thank you very much.
Thanks, Diego. Question?
So, thank you very much for the sparring time. I have a question about how you, because as you said, in healthcare we have the issue is that we don't have enough data.
Yeah.
And like you said, one of the ways to do that is to expand the data that we have by rotation, by adding some semantic data. But the issue is that, rotation makes sense because you don't want rotation to affect your data, but we still don't know if in reality, if other pathologies are, we can generate other pathologies or not. So the issue is that although the data looks larger, like you can go from 20 to 200 or even 2000, but still it's generated based on that 20 variation. Mm-hmm. You don't have 20,000 different patients. You have, I don't know, 1,800 variation of 200 data that you have. Mm-hmm. So do you think really that this can help to improve the situation, or if deep neural network is still, I don't know, for healthcare, we should maybe think more about it.
Yes, so that's it's a very relevant question, and well, there are two points to that. The first one is that it depends on the problem. So in my particular problem, I was looking at only people with epilepsy. So my contention was, okay, let's try to predict neural density in the whole population. So that was a very broad statement that I had to, criticize and reduce to make sure that I had the scope that was appropriate for the data that I had at hand. But having said that, even when I have a very small population, the particular data set that I had was very cohesive. So I have people that have only certain pathology. So whatever assumptions or the predictions I could produce applied to this particular population. So if your problem, for instance, you're talking about pathologies, right? So you need to be very specific about the scope. So you want to be able to predict any brain tumor, for instance, then you need to have samples from any possible brain tumor. But if I'm only trying to predict oligodendrogliomas, then if my data set is cohesive enough and I have sufficient samples that capture the variability of my particular data set, then I can proceed. Having said that, the paper that I show here, the scientific report paper, that they use about 200 patients. So yes, instead of 20. So, but again, they had a broader scope. They were trying to analyze brain tumors. I don't remember exactly the scope, but it was a bit more general, yes. So it's important to take into account the scope and be aware of that.
Thank you.
Yeah.
I had exactly the same question, so let me just add what I was going to ask. Why is it okay to use data augmentation in terms of rotations in training deep neural networks?
Yes.
And if you're using SVMs, you get 4 points sitting on the same place in your 2D space. So that dichotomy has always bothered me. Can you?
Yes. So the idea, in this particular case, the idea of use rotation is to, if you don't use rotations and you only have this, say for instance that I process my histology and I always have coronal slices that are anterior-posterior, right? And those are the examples that I present to my network. So the network becomes really good at identifying that particular orientation. The moment I present a sample that doesn't follow that orientation, the network is going to not be able to learn or to predict anything. So by creating these rotations, I made my network robust to these possible presentations. So data augmentation is important because you want your algorithm to become robust to, for instance, you were talking about depth perception, for instance, right? There are many possible configurations, many different lighting conditions, or many different configurations. Like for instance, we're talking about the lens shape and the intrinsic parameters of the camera, right? So if you have a way to manipulate your data so it simulates different configurations for the different cameras or illumination conditions, then you're making your algorithm better to be more insensitive to those situations. Okay. Having said that, it is always good to have more data. It's always, if you have, instead of 20 pages, you have 200, of course you're going to do a lot more. But the point is, find a way to use the capacity that the model gives you and use it to your benefit.
I think what you're telling me is that one piece of training data is not even complete unless you rotate it. I mean, in 4 rotations even seems minimalistic. I would say, I mean, like in DTI, you have 64 directions, so why not rotate it 64 times to be able to make it sensitive to pretty much arbitrary rotation? So
in this particular problem, you have 2D images, and actually I tried 45-degree rotation, so 30-degree rotation, but when you do that, you have pixels that become background pixels, so you don't have any information. So you have a square that looks like this, and then you rotate it like this, right? In the original square, you're going to have blanks.
Put it in a circle.
Okay, then you're going to solve my problem. So the problem that I had was I was training my network with these random rotations, and then the network learned that it was not the pixels where I didn't have any information were not important, and then the prediction that I was having was like like a lens when you only see the center and then nothing around. So I was having those kind of results. So again, the rotations or whatever affine transformation that you use has to make sense for your problem. Okay. Yeah.
Any more questions?
So, like, as you said, one of the issues in medical is that we don't have enough data, and that results in issues. But maybe there are different data sets in different universities.
Yes.
And because of ethics and like those legal issues, we are not allowed to share it, and like there is a lot of paperwork to be done. So I was wondering if one of these shares can be a legal support. So maybe something else that like allows university to after identifying the data to share them easily. I know there are ways right now, but for like maybe because now we have this initiative because of deep neural network, maybe it helps us to put more time and effort on that.
Yes, thank you. Just reminded me of something very important. So forget about getting data from other universities, right? That's a huge.
Yeah, that's a lot of. Yeah.
It has so many layers of complexity that.
Almost impossible.
Yes. But what we can do now is we can share models. So think, for instance, of a network that has been trained to recognize tumors in your abdominal area, like tumors in your liver, for instance, right? So you can use that network as the initial point to train your network to detect brain tumors. So one of the big problems with deep learning is that you always have to start from scratch, right? So when you start from scratch, you need a network that learns every little thing. You have so many parameters to adjust. But this could be a good starting point, and that's actually one of the elements in that slide that I show you. Let's see if I can show you very quickly here, sorry.
You can generate MRI images, like, which is not real.
Here. So transfer learning. So this is another area of research. So you can start with that network, and then you can fine-tune it with the small data set that you have. So I think that this is something that would be very important for us, like later on you guys when you graduate or you move to a different institution, if we can share models, then we can help each other out. And this doesn't go against any, I don't see why we shouldn't, the same way you share my code or I share your code, this is the same. So we could share models, and then you have pre-trained network for something very specific in the medical domain, in imaging, then why not?
That's good.
Thank you.
Thank you.
Okay, thanks again. Let's take a 20-minute coffee break. Coffee's out this way this time.